Monday. Just to let you know what a panic we're in now. The semester final is due 2 weeks from today. Wow. That's how close we are to the end of the semester. So if you're missing assignments or need to redo some assignments or tests on Buzz, now's the time. Actually, the time was probably already passed, but now's the panic time. We're already past the time that you should have had that done. But some of you need to get some things turned in, and a lot of you are in good shape. Kudos to you. Fabulous. A lot of you in good shape. But yeah, there's a few folks that need to get some things turned in so that this semester will count. Right? You don't want to have the whole semester and it did you no good. But yeah, get your stuff turned in, and we'll all have a happy Christmas. Right? Merry Christmas. Good time and all that. But we got to get some assignments turned in first. Let's look at this week. What do we have? I've already changed some things from when I assigned them this morning, but it's all right. We're going to look at what's left. Algebra 3. Why don't I have 100%? Oh, I was just playing with this. I got to go back and retake my 4.04. I just answered one question and didn't finish it, and so I got 20%. Here's what we have left. We have graphing exponential functions and graphing logarithm functions that are due this week. Then you have the Module 4 test. It's just open response. I think there's 4 questions, or I'll have to look. But we're not doing the whole bunch of multiple choice and open response. We're just doing the open response portion of that for Module 4 because we also have the semester exam. So that Module 4 test, I'll give you to that Sunday, but I wouldn't take that Sunday because you also need to get the final done. The final will be open to you on the 15th. That is 10 days from now. That is next Thursday. Next Thursday, you will have the final, and it's due on Monday, 2 weeks from today. Due on Monday. You'll have the Module 4 test. It may be open now. I'd have to look at it. I'll make sure it's open before next Monday in case you want to finish Module 4 assignments and do that at the end of this week. So all you have left is the final. That's fine too. But I'll make sure the Module 4 test is open for whenever you want to work on it. But this is it. We're getting to the end. You might want to take that Module 4 test so I can grade it soon. So you kind of let you know where you need to be on the final, right? If you have this what if up here in your grade screen, get the what if. You can say, okay, let's see. Let's say that I finished. These are just practice grades at the bottom, so they don't affect anything. But this is your evidence of learning grades. So if I get down here and say, okay, let's say I get this assignment and I get a 60% on this, and I get an 80% on this, and let's say I bomb this test. I get a 10% on this test. So what's my grade? I have a 92. So it's like, well, how do I have to do on this final then? What if I make an 80 on the final? I can go up here and recalculate. It'll bring my grade to an 89.94, which would round up. So I can make an 80 instead of it. What if I made a 70? 88.6. I'd have a B, then my A would drop to a B if I get a 70 on there. If I get a 75, I still had a B. But that what if can tell you. And if you're wondering, well, what if I went back in this 20% when I got 100 on that? Would that push me back up? Yeah, they get me back to a 90. See, I can go back and play with any grade and say, what if, and recalculate it. And they'll say, well, your score would be this if you scored that on there. So I know a lot of times at the end of the semester, you're trying to figure out, what do I need to get a B? What do I need to get a C? Or, hopefully you're not saying what do I need to pass, but there may be a few. But you can go into the what if on the grade screen. But there you go. So we are going to look at these two, graphing exponential and graphing log. So shouldn't be too bad. There was a 4.08. I've decided we're not going to do 4.08. So we will just work on graphing exponential functions and graphing logarithmic functions. All right, let's look at these lessons. Oh, this was pretty cool. Sierpinski was a Polish mathematician. He worked with fractals that gave us the Sierpinski triangle. So if we're here, let's see how to pronounce it correctly.
Sierpinski.
Sierpinski, it says. Okay. So have you ever seen a Sierpinski triangle? Let's do this. I'm going to mute it.
One method of creating the triangle.
So the Sierpinski triangle, you create a triangle. Let's make this mark. And then it's an equilateral triangle. So all three sides are the same length. So if you draw another one inside of it and remove that, the points of that triangle are at the midpoints of each side. That's exactly the middle. So then you have three triangles. So you can do the same thing with the three triangles. Create an equilateral triangle inside. All three sides the same length. Do that with all three of these. And now you start out with one triangle. You went to three triangles. Now you're at 9 triangles once you remove these three that are at the midpoints of all those, because it's an equilateral triangle. So now we have 9. And we can continue doing this. Each of those, take an equilateral triangle out. Now you have 27 of them. Then you can go into there and remove equilateral triangles. Now you have 81 little triangles there, and so on and so forth. You continue, and this is called Sierpinski's triangle. All right, Sierpinski's triangle. It's kind of cool. So this lesson, what's the average rate of change vary on an exponential function? What effects does having a constant have to an exponential function, and how can they be utilized to fit existing data? This is saying, all right, mathematically, how does Sierpinski's triangle mean? Well, it's an exponential function. If we look at this, and I'm going to, again, mute it, so we'll just talk through it. It uses the exponential equation f of x equals 3x for Sierpinski's triangle. Because at the very beginning, when x is 0, before you've done anything, right? So if you substitute 0 into there, 3 to the power of 0 equals 1. And that is the first level. We have one triangle when we start Sierpinski's triangle, when you start drawing that. So you have one triangle in there. But after the first step now, after 0, now the first step is to add one triangle in there, one equilateral triangle. So you would say, all right, so it's step 1, when we put one equilateral triangle there and remove it, 3 to the first power is 3. So we are left with 3 triangles after we do that first step. 1, 2, 3. Now the second step, when now we do this again, we take the equilateral triangles and we put it in there for the second time and remove all of those, x becomes 2. This is our second step in there. So when you have f of 2 equals 3 squared, 3 times 3, 3 squared is 9, right? So f of 2 is 9. When you do that second step, now you have 9 triangles. So this Sierpinski's triangle represents the exponential equation 3 to the x. Because however many steps you do, you can put the substitute into x. Now the third time that we do this out of here, 3 to the third, there's going to be 27 triangles after the third step, because 3 to the third is 27. So if you take out those, now you have 27 small triangles. There it is. It counts them all off for you. And so on and so forth. 81, 243 after the next one, and it will just continue in that method. So Sierpinski's triangle is just kind of it's an exponential function. Kind of cool. So graphing the exponential function, the domain is all real numbers, but what's the range? So let's look at the graph. Here's the graph of 3 to the power of x, right? So it never goes below the x-axis. It'll never get to 0. If this is -5, it's a very, very small number, but it's not 0. It's not less than 0. So it'll never touch the x-axis, but it gets to be a very small number. When x is -1, it is 1/3. When x is -2, it's 1/9, and it's 1/27, and it's 1/81st. And so that 5 is negative. It's not negative. I mean, it's 1/8 over 243. That's a very, very small number. And it gets smaller and smaller and smaller. When x is 0, we're at 1, right? Because 3 to the 0 power. 3 to the first, we're at 3. Then we're up at 9 when it's 3 squared. Then we're way up to 27 and 81. So that is the graph of 3 to the x power. So the range is basically y is greater than 0. Not greater than or equal to, because the y will never be 0. It will never touch the x-axis. But the range, all the numbers that can be produced from all the domain values, is y is greater than 0. So let's see. This is look at the negative numbers we was talking about. When x is -5, it's 1 over 243. -4, it's 1 over 81. -3, it's 1 over 27. So it never gets to 0. So this has a little exercise that we can play with it. So if we have 3 to the x power, if we have a base between 0 and 1, all right, let's say we have a base between 0 and 1. Our base is going to be, well, between 0 and 1. So that's a negative. Say it's a half. That's our base. That's the number that's being raised to the power of x. That looks like that. If we have a base greater than 1, we just had 3. All right, there was that graph of 3. It goes through 1, it goes through 3, it goes through 9, and continues up. But if it's less than 1, if it's just a decimal or a fraction, we could have 1/2. It's the same number. Then it reverses. It's a reflection over the y-axis of the other one. Because these, there we go. This goes up to 5, so we can have up to 5 and down to 1.5. But they're basically a reflection of each other in a lot of ways. It just gets taller and wider. If it's 1, it's just 1 to any power. It's just a straight line if it's 1 raised to a power. But anything below 1 is just how steep is it. Is the smaller the decimal, the more steep it is. The bigger the decimal, 0.7, 0.8, 0.9, the flatter it gets. So these are a reflection of each other. 1/2 and 2 are a reflection of each other. All right. So think about it. Move the point on slider B. What base exponential is greater than 1? Okay, we did all of that. Play with that. Let's go look over here. This is another video, and then instead of doing the video, because these video guys, but let's review exponentials here. I'm going to put it up on paper. So f of x equals 1,000 times 1.25 to the x. Okay, so this is an exponential equation, right? We're going to review this because it's important to know how this works. So we'll have a review. So if 1,000 is our starting value, right? That's our starting value. So what's happening to this starting value every time x goes up 1? If this is years or months or whatever, when x equals 2 and x equals 3. This is getting larger because as we saw in the graph, if x is greater than 1, then the graph looks like this. It's getting larger. If this is greater than 1, it's getting larger. It's going up. And this is getting larger by 25% every time the x goes up. Larger by 25%. If we had the number in the base number that was smaller than 1, it's just 0.5 to the x power, right? We saw that graph. It's going down. It's going down. The graph is less than 1 if the base is less than 1. So this one's getting smaller. And in this case, by 50% each time. All right, so anytime the number being raised to the power of x is larger than 1, Think about the graph. The graph is going up. It's getting larger. But if this is smaller than 1, the graph was going down. This is getting smaller. So if we wanted to write one where our starting value, let's say it was getting smaller by 30% each time. Smaller by 30%. Well, we would have to do this for 0.7 because that's how much we have left. We start with 1,000 and we multiply it by 0.7. So when this is 1, this would just be 0.7. That means we have 700 left when x equals 1. When x equals 1, it's going to equal 700, which would be smaller by 30%. We started with 1,000. We dropped to 700. We lost 30%. So this is what's going to be remaining each time. This is what's left. So if it's getting smaller, what's left? If I lost 30%, I've still got 70%. 700. When x equals 2, first I lost 700 there. Now I've got 70% of this left. So I have 490. I've got 490 when x equals 2. And so on and so forth. So that's just a review of exponentials. But we tied it with the graph. Now we can see it visually. It's going up. It's going down. So we knew that from looking at it before we graphed it. We were playing with that. And that's what he talks about, the same type of things in there. So we're also going to talk about what happens when you add a number to it, plus k, or if we add it inside. So this is if the p is positive, you could have a coefficient out front, like this 1,000 that I had. You know, this 1,000 that I had, if that was negative 1,000, that would flip the graph upside down. That was negative 1,000, and we'll look at that too. So as you can see right here, if the p is positive, the coefficient out front, then if b is greater than 1, it goes up. If b is less than 1, it goes down. If the p is negative, there's a negative out in front of the equation, it just flips it upside down. And it still goes towards whatever the k is. In this case, y equals k. Whatever the k is what it's going to go towards. Y equals k. In this case, it looks like, k is 1 or something. Just a little bit above there. So here's an example. Describe the y-intercept and the end behavior of the following graph. Okay, well, the y-intercept is right there at -1. That's the y-intercept. It's at 0, -1. The y-intercept is -1. Obviously, the k must be -2 because this goes towards -2. So the end behavior, the graph starts at infinity and on the left and goes down and approaches -2. It never touches -2, but as x gets larger, the y approaches -2. Let's see what they say. Y-intercept 0, -1. The graph starts up on the left. You can say that instead of infinity. You can say up on the left, and then decays downward and gets close to -2. End behavior. That's describing the end behavior. Starts up on the left, decays, goes to -2 on the right. The average rate of change. Some of you guys still struggle with the average rate of change. So let's look at this. Juan's got a job that pays him $9 an hour. He worked 14 hours. He makes $126. Well, his rate of change would be $9 for every 1 hour. If you divide 126 by 14, it equals 9. That's the average rate of change. For every time x changes 1, how much does the y change? The x changes 1 hour, he gets $9. 1 more hour, gets $9. Another hour, he gets $9. That's the average rate of change. But if you had something like a skier going down here, the rate of change is different in all these places. But if we just look at the average from when he started up here to when he got to the bottom, if we had the height, 1, 2, 3, 4, 5, 6, maybe 7, maybe he's at 700 feet, and it takes him 1, 2, 3, 4, 5, 6.5 seconds. We could divide that, and the average rate of change is for every 100 feet, he went this much. All right, so we could do the average rate of change. Let's look over here. Here's another one we can play with. And it's got vertical, horizontal, and coefficient. So the coefficient, the A out front. Well, first let's choose the H. 2 to the X power. Yeah, let's see, coefficient. Oh, because the coefficient, when the coefficient is 0, then the whole thing equals 0. That's why it's just a flat line. But let's say the coefficient is 1. So this is 1 times 2 to the X, and we haven't changed anything else. So this is just the graph of 2 to the X. And it's a little bit off, actually, because that should go right through the 2. That should go right through the 1. That should go through the 4. The graph's just a little bit off. But vertically, that would be the K back here. If we put a -1 on it, it just moves the whole graph down 1. Because it's something we're adding on. See, it shows that -1 added it. So whatever the Y equals, we just subtract 1 from it. Subtract 2 from it. Move it down 2 from where it was. We can raise it up 2.5. We're going to raise it up, put up 2. So instead of going through 1, it goes through 3. Just move back down to 0. So there's the original. Now horizontally, if we added something to that X, it's got the X minus H in there. If we made that an X plus 1, it brought it over here where it goes through the 1 on the right. Horizontally move it 2. Now up here, notice it's subtracting. The equation says X minus 2. Remember, it does just the opposite when you put it with the X. -2 moves it to the right 2. Now it goes through over here. It goes through 2 over here. We move it the other direction, make it a minus. Now the equation says X plus 2, but we've moved, instead of going through 2 there, 1, 2, it goes through 2 over here. Instead of going through 1 there, it just moves left 2. So when we put it inside the parentheses with the X up there, it's going to move it left and right. And that's probably, there's some more examples of that. That's probably easier to see on Desmos. But let's do it on Desmos. And let's say, okay, so we have just a coefficient of 1. We're not going to do much with that yet. And this is 2 to the power of X. So there's the graph going through 1, going through 2, going through 4. It goes through 9 up here. When X equals 3, it's 9. Oh, where am I at? Oh, I mean, go through 8. I'm sorry. 2 to the 3rd power is 8. So it goes through 0.38. But when we put something on the end, if we say -3, it just goes down 3 spaces. Now, instead of going through 1, it goes through -2. Ooh. 1, -1. It used to go through 1, 2, went down 3. So let's take out the 3. Now, if we went back up here to the X and added something there, add +3, not equals 3, +3. It just moved it 3 to the left. From over here, yeah, let's put the original one on it too so we can compare it. Equals 2 to the X, because that's what we had originally. Oh, not X to the X. 2 to the X. So we can see it just moved over. Every point moves over 3. This point here that's at 1/2 is now over here at 1/2. All right. Let's say, what if we have Y equals, I'm not going to put the coefficient of 1 out there because multiply it by 1 doesn't do anything. 2 to the X. Keep doing that. X to the X plus 5. Well, let's not do 5. It's almost off the screen there. Plus 3. That's where it just raises everything 3. Instead of getting close to 0 here on the Y, it's getting close to 3. It never goes below 3. It never touches the 3. It just gets closer and closer and closer. If we go way over here and look at it, we're at -70. -70. Well, if we zoom in, it says it's at 3, but it's not. If we zoom in.
Mr. Brock, what are you looking at? Because I can only see, I don't see anything, changing.
Oh, it's not showing here. Okay.
Oh, that makes more sense. I was really confused.
I'm sorry. It's showing the wrong screen. Hold on. Let me get it over here. Thank you for bringing that up. It was showing the wrong screen. Y equals 2 to the X. Oh, I keep going 2 to the x. Thanks for asking about that. So there's the 2 to the x. You know, it goes through the point 0, 1. It goes to the point 2, 4. Yeah, I'm going to take off these extras. Let's make it go by ones and don't put the minor ones. Step one. It's not letting me do the steps there. All right. Open that up again. Well, it's not letting me do step 1 on there. Don't let me type it all. That's interesting. Okay. I do need the minor lid since it's not going to do anything. So there's the point 1, 2. So if we add -3 at the end, let's do it over here. Why? Oh, it's not letting me type. This is weird. I'm going to close this out. Something weird's going on with this. The computer's locking up on me, apparently. Because when I click, nothing happens. Okay, well, that's not right. Oh, wait. Now maybe let me do this. Hold on. There we go, -3. Let's put our original one up there too. Y equals 2 to the x. We see it just went down 3. We can see this point here. Oh, I bet it lets me do this now. I could probably do the step 1. Yeah. Okay. See, it starts up here at 1, 2, but it goes down to 1, -1. Just drop 3. Just adding that 3 on the end. If we put a coefficient in the front, let's compare it to the original. Let's turn off the red one. What happens if we put a coefficient in the front? So we had, we'll go ahead and put the 2 in parentheses since I'm adding a coefficient in the front. There's the 2 to the x. It's the same thing. But if I add a 3 up front, it goes up. 1 times 3 is 3. This is at 2. So 2 times 3, it goes up to the 6. So basically, it just makes it go up faster. Accelerates it. If this is less than 1, let's say it's 0.3. Now, instead of at 1, it's down here at 0.3. Instead of 4, it's down here at 4/3 or 1 1/3. Well, 1.2, and okay. So 0.3 of it. If we make it at 9, it's going to be really steep. See, it jumps way up there to 9 real fast. So let's just double it too. Let's say that we've got, let's look at this one. Y equals 2, raise the power up. 2, raise the power of x minus 5. So it just takes this 1 and moves it over to 5. It takes this point at 1, 2, and now it's at 6, 2. It just adds 5 to the x value by putting -5. If we put +5, it moves the other way. -5 plus 5. All right. So that's what this was playing with, was just changing those numbers to see how the graph changes. And then they give you some examples you can go down here and look at. If we have less than 1, it's a decay. It's going down 1/3 to the power of x. And you need to put that in parentheses if you type in Desmos. Otherwise, it'll get confused. It won't take it all to the power of x. The whole 1/3 needs to be. Graphing exponential function. So here's some data collected, and it wants us to use this to work through the example. So the coefficient values. Use the arrow to drag the blue points A, B, C, D, and E to match the coordinate points from the table. So we have the point -5, -1. So we'll put A at -5, -1. Oh, -1, sorry. All right, -5, -1. And then we have -2, -1. And we have 0, -2. And we have 1, -3. And 2, -5. All right. So now what equation would we need to make that graph. Use the sliders to adjust the different pieces of the exponential function. Well, let's see. We see -2 is the y-intercept. So this is x minus h plus k. So let's see if we take that. Well, we need an exponential first. So our coefficient, let's try putting it at 2. And let's say this is, can't be 1. Oh, it needs to be at negative, doesn't it? Because we want it to be upside down. So there's -2, but we need it to be lower because it looks, see, this is going to -1. So let's change our k to -1. So it gets closer and closer to -1. But it looks like, let's see what our h needs to be. Do we need to move our h over? Oh, is it -1? That's pretty close. -1. It just doesn't quite get that one. I'm not sure if we could change our coefficients on it now. I think that's the closest we're going to get because we put a -3, it moves off. -2 seems to be right. This one's just a bit off. And it could be that they rounded that because both of those shouldn't be -1, I wouldn't think. That's probably a fraction that's bigger. But let's check and see what they get. We've got 2 times 2 to the power of x minus 1 minus 1. They got 2 to the power of -2 times x minus 1 minus 1. So you got the same thing. Theirs doesn't touch the b either. The b's off just a little bit. This is one possible function. It's possible to find a better fit, but this is a good fit. Close as possible to those data functions. And that's the end of the lesson because there's the lesson summary. And we didn't talk about the average rate of change. I want to do that real quick. Let's use the original function here. Let's get rid of these. All right, so we're getting rid of those. So using this, if we want to talk about the average rate of change, the average rate of change, it depends on where we're looking at because it's changing all the time because the average rate of change is the same thing as the slope. Well, the slope at here is different than the slope here because it's very steep up here. But as we go down, the slope's getting close to 0 down here, right? So the slope changes everywhere. So when we talk about the average rate of change, usually asking between 2 points. So between 0 and 2, let's say between 0 and 2, what is the average rate of change? Well, here's when it's 0. So we have the point 0, 1. We'll label that. And then when it's 2, we have the point 2, 4. Label that. So what's the average rate of change? What's the average slope? The slope up here is bigger than the slope down here because this is closer to flat and that's getting steeper. But there's an average between there. And so the way we figure the average, let me write those 2 points down. It's rise over run, right? 1, 2, 3 is our rise. 1, 2 is our run. So that's 3 halves. 1.5 is our slope, 3 halves, because the rise over run. We could also calculate mathematically. Remember the y2 minus y1. How much do the y's change? How much do the x's change? So the y's is, I'll say 4 minus 1, because that's the y values. This is 2 minus 0. 4 minus 1, that's 3. 2 minus 0 is 2. We still get 3 halves. That's the average rate of change between here. So we could write a line, y equals 3 halves. That's the slope, x. And then plus 1. 1 is where our y-intercept is. Look, and it'll go right through those 2 points, which means we nailed the slope. That is the average rate of change is 3 halves. But what if we want to look, let's turn that off. What if we want to look between the points of 0 and 3, where x is 0 and x is 3? Well, let's see. At 3, this is 8. So the average rate of change there. Well, it's not 3/2, see, because that doesn't go through the 8. Well, let's see. Rise 1, 2, 3, 4, 5, 6, 7 runs 3. So if we change this to 7/3, now let's turn it on. Oh, that is the average rate of change between those 2 points is 7/3, which means when it goes up 1, it rises 7/3. So which means we would have the point 1, and instead of 1, it'd be 10/3, which because that's 1 plus 7/3 is 10/3. And then it would go up another 7/3 up to there. So that would be the point 2, 13/3. Oh, not 13. I got to raise it 7. 7/3, 17/3. Don't like the parentheses down there. There we go. So I raise it another 7/3. So when I add 7/3 to 10/3, I get 17/3. So every time x goes up 1, y goes up 7/3 and 7/3 and 7/3 up to 8. That's the average rate of change, which means when x goes up 1, how much does the y go up? Well, in this case, it's 7/3 between those 2 points, which is 2 1/3. So it's a little over 2. The slope's a little over 2. Of course, when we get down here, now it's much smaller. Slope's going to be less than 1. It doesn't even go up 1, because from here, this is 0.5. So it goes up 0.5 and over 2, over 1. I mean, so the slope is, average slope is 1/2 between -1 and 0, because it goes up 1/2 and over 1. Average rate of change, which is the slope. So you can use that anytime, average rate of change. What's it go up and how much does it go over? Or subtract the y's and subtract the x's and put the y on top of the fraction. What effect does adding a constant have to the exponential function? Right, that's when it got flatter or got steeper. So opening, showing the graph of 3 to the x in the summary. And the key features is the y-intercept, the end behavior, and the average rate of change just talked about. And a function said to be best fit if it passes closest to the given points. We had that one that we had best fit. All right, and then there's some practice problems for you in the lesson. You try, and it'll tell you if you're correct or not. There's 2 different ones. So it says, which function will be best for the given table? We got a table where when x equals 1, it's 2. When x equals 2, it's 3. And when x equals 3, it's 5. So which one of these would it be? Well, let's see. 2 to the x plus 1 plus 1. All we do is plug this in. 1. Let's plug 1 in for x. So it'll be 2, and 1 plus 1 is 2. So 2 squared plus 1. Well, 2 squared is 4 plus 1 is 5. It can't be that one because it says we end up with 2. We don't end up with 5. So let's plug 1 into the next one. 2 plus 1 is again 2. So 2 squared minus 1. That'd be 3. Again, it's not 3. How about 2 to the x minus 1? So 1 minus 1 is 0. So this would be 2 to the 0. 2 to the 0 power equals 1. 1 plus 1 is 2. It could be this one. But let's check this one. 2 to the 1 minus 1. 2 to the 0 power is 1. Minus 1 would be 0. But it has to be that one. All we had to do is check number 1. Let's go ahead and check number 3 just to be sure. So number 3 says, x equals 3. 2 to the 3 minus 1. Well, 3 minus 1 is 2. So 2 squared is 4 plus 1. Oh, we do get 5. So that should be right. Good work. You identified. Just by plugging the x in. If you have a function, you have an equation, anytime you have an equation and you have an x, y, and you're trying to figure out which equation, take the x's, substitute them into the equation and see which one equals the f of x. Which one does the y equal? Does f of x equal 2 when you substitute 1 in for x? Does it equal 3 when you substitute 2 in for x? There's only one of them that'll work for. So, and there's another one you can try there. So I'll leave you that one. So that's got a half or a 2 out in front. Again, all you do is substitute the 1 in there and then do the math. See what other practice problems they give you. Graph and write a description of each of the functions. So they want you to graph f of x equals 4x. You do that on Desmos. You can do it on paper if you want to make a table. But it's easiest just go ahead and say, okay, 4 to the x power. There's the graph. It says f of x. You can do f of x, but 4 to the x power. And it says describe. Write a description. What do we describe? It talked about the y-intercept and the end behaviors. This crosses the y-axis at 1, at the point 0, 1. On the left side, it approaches x equals 0, or y equals 0. It approaches the x-axis or approaches y equals 0. And on the right side, it continues to infinity. Let's see what they say. They graphed it. This is an exponential function of base 4. It's steeper on the right side of the y-axis than an exponential function with a base of 2, for example. Okay, so they described it a little differently. They should have given the y-intercept at the base. All right, so here it says assignment. Okay, let's go look at, oh, it is something to submit. Okay, let's go back here and see what the assignment was, because apparently the assignment is here at the end. Complete the graphing exponential functions. It says this is an auto-graded, so let's look at the graphing exponential functions. There it is. Oh, I'd already started it, so that's why I said continue. So this says which graph models this function, and it gives you the equation right there. It wants to know which one of these graphs it would be. And they're all very different. So you should be able to tell, well, it starts with a negative, it has a 4, it's 2 to the x power. Which one of those is it? And this says if you had f of x equals 2x, and then you said, what's f of x plus 1? Well, that's just adding a plus 1 on the end. Which one of those 4 graphs would it be if you just added 1? Which one describes the key features of this graph? Gives the y-intercept, says what happens on the left, says what happens on the right. For that graph, which one of those would it be? What's the average rate of change from x equals 0 to x equals 2? From x equals 0 to x equals 2. What is the average rate of change? The rise over the run. And then which exponential function is best for this table? And that's what we just did in the last one. We just substitute the x in and see if that equals 10. Substitute the x of 3. Does this equal 10? One of those is going to equal 10. If more than one of them equals 10, then you need to check the next number. Okay, just between the ones that equal 10. They may go through the same point 310, but then they'll be different. So that is the assignment there. The next one is just graphing logarithms. That's a simpler, shorter lesson than what we just had. It's just got 1 through 4. So this little exercise you can do on which one represents an image reflected over a y-axis. So you got to look at those and figure out which one of those 4. Got 4 of those for you to practice. So this time you're going to say, how can logarithms be graphed with different bases? And how do transformations affect logarithm graphs? So let's say could be a reflection of an exponential function. The exponential function, y equals 10 to the x, is here on top in blue. The logarithm, remember, a logarithm is an inverse of an exponential. Inverse. So when you graph it, it's going to reflect over that line y equals x. So y equals log 10 of x, which is how you rewrite that as a log, would graph this way. It's exactly a mirror reflection of the exponential over y equals x. All right. So, all right. So open the graphing program or calculator choice. We're going to do it on Desmos. Are we clear? Let's clear all those out. And here's our lesson. Our lesson's 1 page, and there's the summary at the bottom. And wants to know how you can graph it with different bases and how the transformations affect it. So if we have log 4 of x, log base 4, even when we go to Desmos, Desmos doesn't give an option. If we say y equals log, it doesn't have the little number at the bottom that we can put in there. It's saying log of what? Log of x. There's just log of x. This is base 10 because we don't have a choice of changing that. I'm going to go back to lesson summary. But what if we had log x divided, that we want base 4 log x? Well, we can say, okay, well, I want log x in parentheses divided by, I'll hit the divided by symbol, log 4, right? Remember our change of base formula? You can just take the x and put it on the top, the argument, and then put the base on the bottom. So this is the log of x for base 4. Notice when x equals 1, it goes through the point 4. Before we had that, let's go back to the other one. Log equals, y equals log of x. This was just log of x. It goes to the same 0.10, but this doesn't go through 1, 4. For 4, 1, it goes through 10, 1. Because when the log equals 1, log base 10, that would be 10, because 10 to the first power is 10. On this one, 4 to the first power is only 4. So it's a higher log graph than the base 10. So that's how you do that. If you have log base 4 and you need to graph it, you put the argument, the x, on top, and then you put the 4 on the bottom. So looking at the practice problem they give you 1, 2, 3, 4, 7 problems. Log 15x. Graph this and then check your answer. So we need to graph log x base 15. So we can just change that to a 15. Oh, look at that. See, it doesn't hit 1 until way over here at the 15 now. 15, 1. Let's check ours with theirs. Well, they don't even go over to the 15, but you can see at 5, it's still not there yet. It's still low. So that looks like the same graph that they have. So graphing log is a very short lesson because you're not going to do those by hand. You can, but you got to figure all those logarithms, and that's a lot of work and a lot of calculator work. So this is just saying use Desmos or graphing calculator, whatever you'd like to use, and just make sure you know how to graph those. Let's look at what the assignment is for this, what it says. Oh, this is the assignment that's at the end. I knew one of these. Let's go to the last page, page 4, see what the assignment is, because it's something you got to submit. Okay, assignment. There's 2 options, work alone or work collaboratively. We're not going to go into groups because virtually that's a lot of work, and you got to have meets on your own outside. Choose option 1, work alone. And here is what it says. If you ever swam in a pool and your eyes begin to sting and turn red, you felt the effects of incorrect pH levels. pH measures the concentration of the hydronium ions and can be modeled by this function. So they gave us an equation right there. P of T equals negative log 10 of T. T represents the amount of hydronium ions, and PT is the pH level. So this is the pH level. This is the formula for the pH level. So it says water at 25 degrees Celsius, that's pretty warm, has a pH of 7. Anything less than 7 is called acidic. And above that is basic or alkaline. It has above that. Seawater has a pH just more than 8, where lemonade is about 3. Lemonade's very acidic. Create a graph of the pH function either by hand, if you'd like to do it by hand, or using technology. So you would need to take a screenshot of your graph and locate on your graph where the pH value is 0. The pH value, that would be the y, right? Because this is the pH where the y is 0 and where it's 1. You may need to zoom in to figure out where that is, where the x's are, that's 0 and 1. You may not. But basically, you're just going to put this in the Desmos. And instead of t's, you probably use x's because Desmos uses an xy graph, not a TP graph. So that's number 1, is to create the graph and locate where it's 0 and 1, or the pH value. Then it says the pool maintenance man forgot to bring his log chart, and he needs to raise the amount of hydronium items which is the t, to 0.5. So the t would equal 0.5 in this case. So he can use the graph you created. It says, use your graph to find the pH level if the amount of hydronium atoms is raised to 0.5. It says, convert the logarithm to an exponential function using y. So you would just rewrite this as an exponential function, but you would change the t to 0.5 before you rewrite that. And change the pH, the P of t to y. And then it says the pool company developed new chemicals to transform the pH scale. All right, so they still have the same function. Explain which transformation results in the y-intercept and y. You can graph it, or use technology to graph it, but just show what happens when I put +1 at the end of the graph. What happens when I put +1 with the t, only with the t? What happens when I put a -1 coefficient out front of that? So you can put the 3 graphs of that if you want to show what happens, or you can just explain when I add +1, this happens to the graph. So there's just 3 questions. 3 questions, and most of it you just go graph it. Number 2 is where you have to look to say, all right, if I change the t to 0.5, what I have to rewrite it as an exponential function, changing it to y and 0.5. But that's it for that assignment. So 2 assignments, one's the multiple choice, one you got to submit. It's just 3 questions. So there's not a whole lot this week. That's good. It's not gonna bury you in work this week. So if you are behind, this will give you an opportunity. Remember, our final's due in 2 weeks, people. It's time to get everything turned in because you're going to run into it. So there's not a whole lot for these last assignments. This is the last assignment of the semester. All we have in this is the test for this module and the semester test. So, all right. If you got questions, hang around. Otherwise, I'll let you go. Enjoy your week. This is an A day. I got to update my calendar. It's an A day on Friday, but Wednesday we'll have class if you need to be here.
Let's get out of here. Word to your multiples. Math, baby.